Welcome everyone to Zigtoberfest 2025. It's awesome to see so many new and also a few familiar faces. Before we get started, there are a few things I want to talk about. So first of all, I want to welcome you and maybe talk a few sentences about Zigtoberfest. So this was born out of Zig meetups here in Munich. It was a smaller group. We met with in smaller cafes, but we met at a cafe, but we usually didn't talk about Zig that much. We just drank beer or whatever, Aperol Spritz. And we thought, hey, maybe it would be a good idea to make something a little bit more professional. And then I did a small survey on Discord, got 6 thumbs up. So, okay, then let's do something. Sora, for those who know him, also said, hey, maybe I give a talk. He didn't submit, there were no submissions of Sora, unfortunately. But then Felix jumped in and said, hey, would prefer if we do it in October. So if you want to complain about the weather, you can talk to him. And then, of course, Rene. I pinged Rene, and he then came up with the name Zigtoberfest. So I really want to thank, first of all, Professor Schreck and the University of Applied Sciences in Munich that we can use the location for free. And of course, my girlfriend who will support me today, and all of you for actually showing up. So especially if you give the tickets away for free, you always wonder how many people will actually show up and is it worth it? But I think it's worth it. A few things about me. I do computer stuff and open source, mostly on GitHub. I have a few Zig projects. The thing I'm use the most is a passkey or FIDO2 implementation I use for authentication on Linux. And yeah, that's a little bit about me. So when it comes to organizational matters, coffee, drinks, everything is free. If it runs out, then it runs out, but just help yourself. Please keep the rooms clean. I placed a garbage bag there at near the coffee machine, and just use that for your garbage and help me a little bit so we don't have to clean that much afterwards. We'll also record the talks, but this will mostly affect people in front of the camera. A little bit about the location. You can find restrooms or toilets on the other side of the aisle. Down when you walk towards the main entrance on the right-hand side, next to the cafe, which is closed today. And also on every floor for lunch. So we will have 2 talks, then we will have lunch. And for lunch, I would suggest you find together in smaller groups and find some nice restaurant to eat, order pizza, or do whatever you like. I think we have a quite nice agenda for today. So we will start off with a demo of the new Async IO by Andrew, and then Andrew and the Zig core team will do a Q&A moderated by Loris after that. So because there was a lot of confusion with with this talk, unfortunately, Dimitri had issues coming to Germany, so we had to cancel his talk. But we would love to hear what he had to tell us about ODIF. And after that, so after the Q&A, we'll have a talk by Lukas, who's also been here the last time. And he will talk to or tell us more about log-free data structures. Then we will have a lunch break. And after 1.5 hours, so 1:30 p.m., we will meet here again for the second block. We'll have a talk by Loris about how to write better software with Zig. And then we will also have a talk by Rene, you probably all know, about how to run a company on the command line with Zig, LaTeX, Git, and Zap. Then we will have a short 30-minute break. I think this is a great time to open the first beer, maybe not before. And then after that, we will have the last block for today with Next Level Terminal Games by Mario Schallner and talk about how to send all your private data to ChatGPT. Don't know if you should do that, but if you want to, Frank will tell you how. So I'm really curious. And then, so roughly at 6 p.m., the official agenda will be over, and you are free to stay or leave, do whatever you want, but we invite you to stay a little bit longer, chat with people. I think this is a great opportunity if you're interested in Zig to connect with like-minded people. So, and that's it from me. If you have any questions, any issues, then just talk to me, talk to Franzi. We're happy to help you. And again, welcome to Zigtoberfest 2025.
Yeah, hey, thanks everyone for coming. It's nice to see everyone. And if you catch me around later, feel free to say hi. I'm friendly. I will chat with you. I love to see what everyone is up to. So be friendly. And right, okay. So what I'm going to demo for you today is 11 examples where I'm going to walk you through the new async awaits primitives in standard I/O that is upcoming in Zig 0.16.0, which will be released in 3 to 4 months. And there's more to get into, but this is an intro into the synchronization primitives that will then now be available to all of Zig code to use. And because it's kind of an intimate environment, it's okay if someone is kind of lost, you can interrupt me because we have time and this will be interactive. And so in the QA, it's not just QA. We can actually do a little bit of feedback. Like, sometimes in QA, it's not, you shouldn't express your opinions too much because it's rude. It's fine. Here, actually, in the QA, give me your opinions and we can have a dialogue because we have time for it. Okay? So put your critical thinking hat on while we do some of these things. Okay? Okay. So to begin, first, let's try to keep it simple and understand the basics, and then we'll slowly add more asynchronous things into it. So with our first example, there is nothing asynchronous happening here. This is effectively hello world in Zig, where we have our main function. We have our function called do work. Our do work function is actually just going to sleep. I just came from Italy, so now I'm thinking that this is what working looks like, is sleeping. Loris told me that I had permission to make this joke. Okay, so everyone okay on this one? So simple? Okay. So next, we're going to set up a little bit. Still not using async await yet, but I need some tools in my toolbox before we really add the complexity in. Okay? So this code is the same, but now in the setup, maybe this code looks familiar to you. We set up an allocator. Okay? Now this is kind of like setting up an allocator. You set up an I/O implementation. Now in this case, this is an I/O implementation based on threads. So this is not using KQ. This is not using IOU ring. This is not using an event loop. It is a threaded implementation of the new standard I/O interface. And this setup will be the same in all the examples. So now we can focus on our example code, which is the same as last time. So still nothing interesting. We just work, which of course is sleeping. Okay? Is anybody lost so far? This is where we start. Okay, good. Okay, next. What we've done is we've taken this function, do work, okay, and now we're using async await. So what async await means to Zig is you decouple the calling of a function from the returning of a function. So really just think of it like, if a function call, you call it, you wait for it to be finished, and then it returns. With async await, you split that apart. So calling is one thing, and then you can do something else, and then returning is another thing. It's the decoupling of these 2 points. That's how it works in Zig. So this code is the same as before. It's exactly the same because we didn't put any code in between here. So we're still just calling do work, except we split the call into here, and then we're just waiting for the call to finish. And the way that this API works is idempotent. So if I push this a bunch of times, it will have exactly the same behavior. Okay? Anybody confused? Can we move on? Yeah, go ahead. Oh, that's a great question. It starts at line 9. The I/O interface does not guarantee that property. But in this case, that is what is happening. That's right. Yeah. And there will be more elaboration on that later. Yeah. Good question. Let me put the type in and then make sure I'm right here. So it's io.future. This is a type that you need to give it the type of the return type. So, and the return type in this case is void. So this should still compile, I think, unless I messed it up. Okay. So this type, and this type is the same with all implementations. I'm going to stick to just looking at examples for the first part, and then in later, if you remind me again, we can go look at the implementation details. Okay? Yeah. Another good question. You're talking about down here, right? Yeah. Very nice observation. Let me postpone the answer to this question because this example will answer it. And then if there's still a question, then we go back, okay? Okay. Yeah. Yes. Yeah, similar concept. I haven't used them in a while, so I don't remember what exactly the differences are. But I do know that whenever I try to use like the then method or error handling, I don't like it. So that part's different. Yeah. This one. It's a clock. So this is going to translate to yes. Yeah, the suspend one is called, well, I forget, but remind me, we'll look at the clock enum. Yeah. Yeah. Okay. Ready to go to the next one? Nice. Yeah, keep the questions coming. It's nice. We have plenty of time to do interactive. Yeah. Okay. So what we saw is just splitting a function into beginning and end. Pretty straightforward. But let's start to add more like real world situations here. So in the next example, we have two things at the same time. Okay. So let's see what it does. Actually, let me clear the screen so I can. Okay. Now these the work is waiting for 1 second. So if you watch carefully, if you count to 1, 1. It did not wait 2 seconds. It waited 1 second because these operations are happening at the same time. So this demonstrates why using async await is useful, because you can express in your code that you want to do, you can express asynchrony. So the fact is that doing this work here and doing this work here are independent. So you can express in your code that they do not need to wait for each other, and they can be done at the same time. And depending on the I/O implementation that you choose, it may be able to take advantage of that concurrency that you have expressed, and, or sorry, the asynchrony that you've expressed, and make your code run faster, which in this case it does, because we've done 1 second of simulated work at the same time, which means we've done 2 seconds of work in 1 second of actual time. Does that make sense? Yeah. That's correct. Yes. So you don't get execution order when you do these things, and that's the point, because when you express this, you're saying that the operation can happen independently. So then the order should not matter in that case. Right. Exactly right. Yeah. You said no op implementation? You can get this effect by passing f single threaded. Okay. And so to answer your question, this one supports that use case with that flag. We can also, and I will show this example later because it's relevant, but you can also limit the CPU count like this. And I'll do that in example 8. Okay? Okay, so we just saw doing something at the same time. Now let's go to, wait, why do I not have example 4 open? There we go. Okay, so now in example 4, we're trying to make this even more real-world scenarios, because in real-world scenarios, you have errors, you have resources, you have all these things. So in this example, we're simulating an error occurring in one of these examples. So this one, the first letter is H. So if that one we're going to return out of memory. And then so it's the same code as before, except now this one will return error out of memory. Okay, now, does anyone want to predict the outcome if I run this example? Give you a few seconds to think about it in case anyone wants to gamble. Oh, Felix. Bingo. Yeah. So this is a problem. It's exactly what Felix said. So to follow the control flow, so this one starts running. This one also starts running. The first one gets to here, returns out of memory. Control flow comes to here, and this try activates, okay? So then we fail to call this function. So we return from here, and then our leak check detects that we actually leaked this task. So this is a bug. This is a bug. So we have to fix this bug. That's unfortunate, right? Because you would like to write the code this way. Well, if we fix it, we have to write the code differently. Okay? So here's a fix. We have to do the awaits, then we have to try the results. Okay? And the rest of the code is the same. Now this will fix the problem. But it's unfortunate, isn't it? Because I want to write the code the Zig way, where I have I can just try await. This is the foot gun for sure. But this is the correct behavior because the first one, the second one worked. The first one returned out of memory, failed successfully. Okay. Well, here is where cancellation comes in. So cancel is a really, really nice primitive. So here's the change. After you do async, it's very common that you're going to, kind of like if you allocate, you defer a free. If you async, you defer a cancel. And this is a really, really nice pattern because now we can use try await like normal. And not only do we prevent the bug, we also get more optimal code. Because look at how fast it executes now. It's instant. Because the moment that this one returns an error, this try returns. Because this try returns, we run over these cancels, and the one that's still waiting gets canceled. So the cancel is your best friend because it's going to prevent you from leaking the resource, and it's going to prevent you from, and it's going to make your code run more optimally. And one more thing before I call out. Here's the semantics of cancel. Cancel, it's very simple to understand. It's exactly the same as await. Cancel and await are the same, except cancel also requests cancellation. And they're idempotent, just like await. Did you have a question? In this case, because we're using the debug allocator with the I/O implementation, we get that for free, as we saw earlier, because if you forget to await something, then you leaked memory. So that check happens to catch the other thing. But you're hitting at something that's a very nice property that we can do. Because we have a place to store state, we can catch additional resource leaks. So for example, I'm showing you only timing and synchronization primitives right now, but this interface will also do networking, file system. Well, let's just start with networking file system. So if you leak a socket or you leak a file descriptor, then this one can catch this and report it, just like the leak checker can catch leaked memory. Yeah. Go ahead. You can keep going. Yeah. This one, the threaded DNet. Ask me again after the demo, and then we'll go into looking at implementation details. Yeah, we'll switch modes. Okay. Yeah. Sure. Let's take a look. So this is the idea, error defer. I think it should always be a defer. So in this case, error defer will be fine. But because cancel is idempotent, so for example, and it's idempotent with await as well. So you can call await, cancel, await, cancel. It doesn't matter. They're all, after the first one, the second ones are all no ops. So there's two angles here. One is from the readability perspective. The defer is a bit easier to reason about because you just know that after you read these two lines, and how do you read the next line? You know that when we return from down here, anywhere below this defer, we know that this will never be referenced again. It's canceled. It's done. It's almost like you can just stop thinking about these two lines if you have the defer there. And then furthermore, I might just want to return early. Like maybe this function returns an integer or void or whatever. It doesn't matter. Point is, if you use defer, then you can just keep using all the normal control flow constructs for the rest of the function. Everything's fair game. You can use try, you can use return, anything goes. You don't have to worry about it. Yep, in the back over there. You should think of it like a resource, as if you had opened a file or as if you had allocated memory. It's like you've allocated a task as a resource. So maybe you don't defer it because later you're going to return it. That's also valid. Like you might open a file and then return the open file. Yeah. But as you can imagine, this is kind of more structured concurrency. So this would be a good way to start. And then not doing this would be more advanced because you have to, well, if the resource lives longer, then that's more complicated to reason about, right? Yeah. Over here. If in the cancel, you run into. Yeah, what's important to understand is that the cancel is a request. So the work may ignore the request, in which case there is no difference between await and cancel. It really just will then wait till it finishes. But ideally, the request is noticed, and then the work finishes faster. But you do not get a guarantee that the work finishes faster from cancel. You may just wait the whole time. Yeah. Can you store await? Can you defer await? Yes, because yeah, that works fine. The only thing you can't do in a defer is control flow out of the defer expression. So you would not be able to defer try await because of the try, but you could do defer await. Yeah, that's no problem. But why would you defer await when you can defer cancel? Over here. That's a great question. You've halfway invented example 7, but I think the other half of your question, we'll do it again after that one. Okay, yeah. Felix? Oh, this. Yeah, the two errors here are clock unavailable and canceled. Yeah, so one thing I should mention here is that there's now many of the I/O functions have error.canceled in the error set, and this is what you would probably get here, which we don't care about because we're returning. So what this means is that it's a very nice property because your resource management code is handling errors, right? In the case of the error, you free the memory. In the case of the error, you close the file and you shut down all these things. And so because cancellation is an error, error.canceled, you end up going through all of your resource deallocation code as you cancel. And then that that propagates the cancel to your callers. Yeah, was that the answer? Did that answer the question? Yeah. Yep. Yeah, the question is, is this illegal if there's any unawaited, uncanceled tasks, right? This is this would be kind of an assertion failure. If you had any, if you did async and then you never call cancel, you never call await, and then you deinitialize the I/O or the threaded in this example, then this would be equivalent to a memory leak. And it could have correct application specific correctness issues as well. So more important than a memory leak, because maybe you needed that to finish in order to correct your data coherency or something like this. I think that this kind of well, this is an idea that can be considered. This is not how it is currently conceived. And my opinion, my first opinion considering this idea is that it's dangerous because um, the code should be managing its resources, and what you're describing is kind of like a queryable garbage collector, right? Well, okay. I wasn't. I don't have this in my examples, but one of the primitives that we have is a group. So then you make the group, and you can async in the group and forget about it, and then later you can manage the group, and that's your kind of bucket. That's your arena is group for tasks. Yeah. 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 Over here. In almost all cases, you're going to get it for free because you're in your code. You're going to call, for example, like file.read, something like this. Now in file.read, there is a new error possibility, which is canceled. So you're doing work, third party request cancel for your work, your call to file.read now returns error.canceled. If you're just doing try, for example, you're now returning try up your function. You're freeing all your temporary resources or whatever, and you end up returning error.canceled yourself. So then that further propagates up. You see what I mean? So you're typically going to get cancellation completely for free. But you could also explicitly add a cancellation point if you want to. I think you will never need to do this. Yeah. Only in CPU-bound code. Maybe you're processing 100 million objects, and if the iteration modulus 1,000,000 is 0, then you check for cancellation, something like this. Okay, ready to go to next example? Okay. Okay, so we looked at we looked at cancellation, which is the big one, and that cleaned up where are we? That cleaned up our resource management. Okay, so next, yes, so next we're doing something also that you might have happen in real world code. Sorry. Excuse me. You're allocating a resource and returning that resource from your function that is being executed asynchronously. So in this case, we will allocate a string and do work if it succeeds. If it fails, we do not allocate the resource, which means that if you have a successful call to the function, you need to free the resource. You need to free the string. Okay. So now we see why cancel and await are the same, except that cancel requests cancellation. Because now in the defer, we have to handle the success case. So if the call succeeds, we have to free the resource. And in fact, even in the happy path, we go down here and we print everything, we still go up and have to free the resources. So this code is handling both the cancellation path and the happy path. Well, it's handling the failure path, which includes cancellation, and the happy path at the same time. So let's take a look at running the code. Example 7. Okay, so that's just running, again, 2 things in 1 second, except we manage resources along the way. So the point of this is just return value here represents a resource that has to be freed. We managed to free it correctly here. And underneath these two, underneath this block of code, the important point is that down here, we still get to write normal Zig code. We can still use try. We can still use return. You can copy paste code from a function that's not doing async into a code that is doing async, and it's going to work correctly. Yeah. Oh yeah, sure. Like this. Yeah. Is this what you're observing? Sorry, line? Yeah, now it's fine because we properly did our resource management in our defer. Yeah. And we still have the property that if the memory allocation fails here and fails here, we don't bother waiting for the second one because we have the cancellation up here. Yeah. Ready for the next thing? Over here? Yes, but you will notice that this is a I/O implementation specific API. So the I/O interface does not require allocation to be how async is implemented. So this is your answer. It's good. It's good. It's gratifying because it means that the progression is yeah, okay. Yep. Yes, that will be copied. Yeah. So you would want to pre-allocate if it's a large return value. You want to have some different strategy for allocating. Maybe you pass it in as a pointer or something like this, and then you populate it. Yeah. And you can do this. Well, there's many ways to do it, but it's important to notice that with this pattern, you can reference stack memory here, right? You can pass this into, like, this is okay, right? We're not going to use the stack memory because this defer is protecting, because this will wait until this is done. Then we know that this is safe to do. Does that make sense? Yeah. Okay. All right. So let's go on to next one. Now we're switching gears a little bit. So it's time to learn why asynchrony is not concurrency. In this example, now we have instead of do work, okay, we have producer and we have consumer. We have a pipe, channel, queue, however you want to call this, with no buffer. So if you try to put into the queue, you will wait until a receiver can take the item from the queue, and then you can go back to work. Make sense? Now, we're using async to spawn the producer, we're using async to spawn the consumer, and we're passing, we're just putting something in the queue here, we take it out of the queue here, and we print it. So just passing a little token along, just like that, okay? So if we run this succeeds incorrectly. This is a bug, even though it works. To observe the bug, we have to do something like this. We have to go in and edit our, this is the same example. We have to go in and add CPU count equals 1, limiting the amount of concurrency that the IO implementation can offer us. Now, if we take the same code, because it can only have one, it's only using one thread, we deadlock. Because the consumer is, sorry, we have only one thread, and yeah, the consumer is waiting to get something from the queue, and the producer is scheduled to run, but has not run yet. And we're waiting for this one to return, so we deadlock. The problem is that we asked for asynchrony, but we needed concurrency. So in order to fix this, we use io.concurrent instead of io.async. This one can fail. So the setup is the same. We now still have only one CPU available, but now we use concurrent. Now the code is fixed because we correctly expressed that we needed concurrency. And if I add single threaded, which is different than this is passing because the threaded implementation will oversubscribe the CPU, which it's allowed to do with this. When I pass f single threaded here, it will only use one thread. It can never oversubscribe. And so now we get an error, concurrency unavailable from here. So instead of the deadlock, we get an error that we can handle and do the code differently. Yeah. That could be a nice idea. That's not something that I've put in the interface yet. But maybe it could be something that you know at runtime. Because, for example, if you're using a thread pool, you have concurrency up to the pool size. And then if you want more, you have to oversubscribe. And the thread pool does not want to oversubscribe because that's inefficient. But if you ask for concurrency, then it will oversubscribe. So if you're asking, well, do you have concurrency? Then what's the answer? Well, the answer is kind of, maybe it actually should error if the thread pool is full. Maybe that should be configurable. Yeah, go ahead. That's how it's currently implemented. That is a decision that the API, the IO API, could make one way or the other. And yeah, I mean, I'm not sure, 100% sure what should be the final way, but the way that I've made now, what I would like to do is to have people try this out in the real world examples and then tell me, how's this working for you? And so the first proposal or implementation that I'm providing to say, hey, try this out, is this one, where you get an error if you ask for concurrency and you can't have it. Yeah, and you really should use async if you can, right? Because to finally answer the question over here, the other one does not fail because if it cannot allocate memory for the task, it will immediately call the async function right there. Does that make sense? So in this case, it has to run concurrency. But in the other case here, if this memory allocation cannot happen in order to allocate the producer, it will just run this function right here immediately before proceeding to the next line. And that's allowed because this is async and not concurrent. That's why there's no try here. Over here? Yeah, let's try that. This one? So we may have run into an implementation issue here. I may need to examine the threaded implementation and look at how I've done like oversubscriptions and concurrency and things like this. So I'm not sure if this is a correct answer to the question. Yeah. Yep. Okay, so let's run through this. So this one is calling concurrent, in which case the threaded implementation will simply increment a requested concurrency counter and then schedule the producer. And then what'd you say? Oh wait, I also did this. CPU count is 1. Do you think the consumer is running before the producer? Yes, but it is required that the producer will be running concurrently. So if the consumer runs first, then the consumer waits for the get, but the producer is then supposed to be concurrent. So then this code needs to eventually run, in which case this will then unblock the consumer, and then everyone can proceed. Yeah, yeah. This is the end. Do you guys want to come down for the QA? Yeah. Microphone and face the audience.
I was looking at that. Oh, you've got it there. That's a good point. Please hold while I try and clip this on properly. Oh, right. Is there only one? Sorry. So I'm pretty sure what's going on here is that so So yeah, the producer is definitely running, but this put one's going to block until the get one call, I'd imagine, right?
Right.
Depends on your implementation. So then I assume that the async is then refusing to spawn the thread. Like you were saying, this is an implementation thing. This is to do with how the threaded implementation is dealing with async when it's already maximally subscribed.
Yeah, I think I just need to revisit the oversubscription code.
And this is,
yeah.
So this is, to be fair, I don't know how clear the interface documentation makes it, whether this should work. But that's a detail we can hash out.
What is certainly a bug is to do the opposite. So if you put async at the top for producer, then async might decide to run. It does not guarantee that you continue executing the main function immediately. And that's what concurrent also guarantees. Concurrent guarantees that you don't stop. Like if you need to schedule more stuff that will unblock what you just spawned, then with concurrent, you're guaranteed that your function keeps running. But with async, we might decide to just stop there in the single thread case, for example.
Yeah, I think I just realized the bug I made, but that's exactly right. Yeah. What's the question? You want to look at the Q implementation? Oh, like a safety feature, detect deadlock. I don't know if it's possible, because the queue is many producer, many consumer, thread safe, and so maybe there could be another producer somewhere that would put it in there.
I think the more general answer is we do plan to have implementation of async of I/O for testing purposes, where we plan to add more checks and maybe even support fuzzing, so make its scheduling decisions deterministic based on a seed. But exactly what it is that we can catch or not, we don't know fully yet. Can you show? Yeah, can you show the source code? No, we're doing the second one.
There's an oversubscription. Yeah. That's.
Does it not run stuff right away? Can you show it? The implementation of async?
Of async?
Yeah. Because I believe that we do just call the function right away, right?
No, only on memory failure.
Only on memory failure. There we go.
Yeah. To be honest, Felix, I couldn't follow everything you said, but I think this is not too bad to fix. Like, with this example in hand, it's just some bad oversubscription code. Yeah. Yeah. Over here. Select. Yes, I did not prepare an example for this, but now that now we can look at some source code. Here, let me make a big window and then make the font bigger. There we go. So let's look at some of the primitives that we have here. I think that's a good one. So first of all, there's a select function. That's a different one. That's a different one. So I'm sorry, this is implementation code. It's not example code, so it's a little harder to follow. But you call io.select. You give it a union of futures, and then you can switch on the results, and then the one that wins the race is the prong that you can that has the result.
You said you give it a union. said you give it a union, I think you meant you give it a struct and it returns union.
You give it a struct of futures, and it constructs a union with this reflection code, and which then you can switch on to get the resulting future. Thank you. Yeah. Yeah, I did not prepare an example for that one. And then there's also a, so that's if you have, you know statically you have this set of futures, and that's kind of like a syntax you can use. It's more handy. The other one is if you know at runtime, maybe in a loop, you're adding things to a select and you want to know which one wins. So for that one, there's this API where you do give it a union. And the union is the type of return values of the function. I didn't prepare an example for this, I'm sorry. But okay, point is you can construct a select and you can call async on this one. And so you can do this in a loop. And then you can, finally, you can wait to find out which one wins. And you can do this multiple times. And this is a general, this is an abstraction that's built on top of a group and a queue. So you could actually implement this yourself just based on these primitives. So group, let's look at group really quick. Again, this is implementation. It's not example, but group is is a really handy primitive. So it's kind of it's the arena of tasks. So you initialize the group statically. You can call async into the group. I think we'll add concurrent to this too. I didn't add that one yet. And then you can wait on the whole group together. And that's going to be more efficient than doing a whole bunch of futures heap allocated or something like this, because it's just a counter instead of multiple resources together.
One distinction between group and arena, which I think is worth calling out, and to be fair, I don't know if you have actually documented this in your version. I did in my variant of the branch. We've worked on this kind of together over a while. But I think generally we intend that if you have a group and you put a bunch of tasks, start a bunch of tasks in it, asynchronously or concurrently, when they finish, the resources associated with that task can actually be cleaned up immediately, or at least once. Immediately. This is desirable because it means that you can use groups for kind of long-lived things. So if you have something like maybe some kind of HTTP server and you want to spawn like a task for every client that connects, then it's fine and you don't need to keep track of all the individual tasks that are happening. It's fine to just put them in one group, and you're not going to leak resources over time because they will be cleaned up when the individual tasks finish. So that's kind of one distinction with an arena where, if you just keep using an arena forever, it's not magically cleaning up resources for you. You are slowly leaking memory.
Yeah. You want to take this one?
I'm happy to take this one. The short answer is no. Next question. No. So firstly, it's not like you're going to be writing IO implementations all over the place. Like, the fact that you can have different ones is really helpful. We expect there to be several in standard library for kind of testing and debugging, and ones that use different strategies for concurrency. But when you're doing that, usually you're going to be writing, a big file with that implementation. So you don't really gain anything from being able to declare the functions in line. In fact, all you get from that is 2 extra levels of indentation, which doesn't really help anyone, compared to just declaring it in the file. Also, Andrew doesn't like anonymous functions, and so he made this decision a while ago, and I don't think he's going to change his mind on that one.
Oh, it was anonymous function syntax question. Sorry, I thought you were talking about function pointers. Okay. Yeah.
Oh.
There's also a question from the chat.
Oh, nice.
Ground Soul asks, is there any performance hits due to passing the IO table around everywhere? Presumably there are a lot of function pointers. Does Zig optimize them anyway?
This seems closer to what you thought was being asked, I think.
Yeah.
You want me to take the? Or...
I'll do this one.
Okay.
So what you're actually passing around is these two things, and it's kind of what this is called a fat pointer, basically. So it's a pointer, it's 2 pointers. So that's kind of what you're passing around. And that's very similar to what you're passing around with allocator. It's the same thing. Actually, let me just show that. So allocator is also an interface, and there's your fat pointer right there. So it's kind of the same thing. And it's the same way of doing an interface. So it's just not that bad for free floating functions. It's just not that bad. And then for in other cases, let me show you. Let me show you just the real world code base. So here's compiler. We have a lot of imports. We have a lot of fields in the compiler. So this is compilation, okay? And here's where we keep our allocator right here. Actually, we have 2. Here's another one. And then here's where we keep our I/O. And we're all familiar with this kind of object, right? Like you have a bunch of functions, and all the functions. Why did I not find a function? There's functions in this file, right?
Using ZLS.
There are quite a few functions in this file.
Yeah.
Well, that's not how function syntax in Zig works.
Oh
There's a
yeah,
name in it.
I forgot function syntax. Let's just search for pub fun. Okay. So the point is, like, all these functions are going to take a compilation, right? There's one. That one's free floating. There's one. You get my point, right? Like if you have, it's very common that you take your context struct as your first argument, and that's where you're going to have your allocator. That's where you're going to have your I/O implementation. You probably only have one for most of your stuff, and then yeah, sometimes you have some free floating functions that are going to have an I/O or an allocator or both. Yeah. Feel free to let me know if they have any follow up on the chat. Yeah, Adrian. I've been calling you Adrian Ariadne, right? Wait. It's okay? Oh, I'm sorry. Techatrix? Yeah. You came in the hotel this morning. I was like, hey, it's Techatrix. What's his real name? And he's like, I don't know. Right. Yeah. 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 What you're describing is a fun trick you can do if you have concurrency, but you can't actually express that pattern with async. You have to use it with concurrent, which, as you pointed out, has the weakness that it doesn't work that way. So yeah, in reality, I think it's better to also have in the I/O interface, we have timeouts. So for example, I mean, sleep is your classic timeout. That's all it's doing. But also in, for example, receiving connectionless packets from the network, you can have a timeout on that. And so, yeah, exactly like you said, this means that this function can be used in like single-threaded, non-concurrent contexts, and also will work fine in concurrent contexts.
So the general idea is you bake the timeout into the operation.
Yeah. Yep. Felix? So that you can, under this condition, would you have access to concurrency where you could do this trick with a timer?
Yeah. But I think this is an implementation detail because yes, but no, my point is you can, let's say that you want, let's say your point is you want, yeah, you want to be able to cancel on a timeout a file system read. That's fine. It's not something that necessarily I think has to be in the interface, because I think this can be done with signals, for example, in single-threaded mode. As in the I/O interface manages the timeout using OS APIs that don't require you to have concurrency. So I'm not sure if that happens in all cases. But my point is that there are some other tricks that can be done. Like, and it's not necessarily that every function needs to have timeouts, but maybe that is the better design choice. I don't know.
it would need to go in the interface if you wanted to be able to have a timeout in an application that did not have access to concurrency. Yeah. Are you thinking of an example of that? Okay.
Yeah, but it is fair. Yeah. Like, let's say that you want to read a file and the file is on a network device that's timing out, and so it's taking forever.
You know, this would be a good time to talk about how cancellation works in the threaded mode. I think that's an interesting topic. Are we trying to fill time, or are we trying to hurry up and finish?
Yeah,
We
we're
should
at the
finish.
end. We're at the
Okay.
end.
Okay.
Yeah.
Well, I'll keep it short then. So you can actually interrupt blocking syscalls by sending a signal to the thread, and then it returns EENTER, and then you can check for cancellation. So you can build this pattern that Techatrix is talking about, where you have a timer, and then you cancel the file system operation.
And you can have, I think there's a timer API, like a timer syscall that can wake you up with a signal. At least on Linux, right? Like timerd or something like this.
But the question, but if you want to be able to run code without concurrency, single threaded blocking, no threads, and you want file system reads to time out, then it does need to go in the interface. Yeah.
It was just a final
No more
at some
questions.
point,
No
but
more
if there's
questions.
any
We're at
more,
the end.
okay.
Yeah. Matt,
Okay.
you wanted to say something?
Yeah, there was just a thing I wanted to end on. If you've got anything else to say, then go ahead. But I just wanted to say this interface is obviously something we've been working on. Where Andrew's been working a lot on the PR to get this initial version in. Pretty much none of these details are like finalized. So I say that partly as a warning. So if you want to start using this stuff, it's helpful for you, go ahead, but know that you're opting into probably some instability in the near future. But also as like an invitation to get involved in this. We are not perfect. There are going to be use cases that we miss. There are going to be design ideas that we fail to consider. If there's ideas you have about how this interface should work, what primitives we should expose, things like that, you could join the compiler development Zulip server and get involved there. That's very active with discussion on how this interface should work, as well as all kinds of details of what we're doing with the standard library and compiler.
Yeah. But bring use cases, not bike sheds.
Yes.
Yeah, more specifically, if you have an idea that arises from trying to use these APIs in a project, and then you run into a problem, definitely want to hear that. If you're just kind of scratching your chin and speculating, yeah, maybe go write some code first and then come back, you know?
Yeah.
So we will get to our second talk for today. If you could please all take a seat. Ah, ich kann nicht fallen. Kannst du? So, like I said, welcome to our second talk of today by Lukas. Last year I said from the highest university of Germany. So location-wise. So, and I will say that again. He will talk to or tell you more about log-free data structures in SIG. And please give him a warm welcome.
All right. Hi from me too. Good to see you all. Maybe again on the highest university of Germany. I'm working at Ulm University, and we also have, like, unofficially the highest tram station of Germany. But I think that's just because nobody else has bothered to check if their tram station is actually higher than ours. So there's an unofficial, like, A4 paper hanging at the station that just says, yeah, highest tram station in Germany. Yeah, thanks for the introduction, David. I'll be talking a bit about synchronization. We already talked about concurrency and async code, and now we will look at how to synchronize access to shared data structures or shared variables, shared segments of memory. If you want to follow along, I also uploaded these slides already. Maybe a short anecdote on that. At last year's Zigtoberfest, I also gave a talk, and for that I registered Zigtoberfest.fun for a single year, and of course I forgot to cancel it, and now I've got Zigtoberfest.fun for another year. So that I don't have just wasted my money, please go to Zigtoberfest.fun, and there you will find these slides and can follow along if you want to. Great. So far, so good. For a little motivation, who of you has already cooked with someone else together? Yeah, that's most of you. And I've also done that quite a few times. Me and a friend group of mine, we do this regularly. And I hope they don't watch the stream or watch the YouTube video, because I actually hate it. It's always like a too small of a space, and there's only one stove or only one pan, and then 4 or 5 people have to work on the same pan and on the same stove, and it always gets confusing. And then one person is cutting the tomato wrong, and another one is doing whatever. So I don't enjoy this as much. I do like cooking in general, but I try to keep it for myself. Sure, I said you need to coordinate access to the shared resource, which is in our case the pan or the stove. This is obviously the same with programming. There we don't have pans or stoves, but we do have shared memory or shared resources that need to be coordinated between threads, so there can be safe access on them. And this is what we will look at today. So just to get started, a little programming example. This is a incomplete stack implementation where, let me get that pointer, where we have a backing data structure which I just chose an array list for, and I implemented the push operation. And traditionally, this would just be self.backing.append and then the value. But in order to see what's going on, I wrote down 3 lines more, which probably is what append is implemented with. So we will start by getting the length of our current data structure, so all items. And we modified the last free slot in our data structure, and then we increment the length by 1. And with that, our push operation succeeded. So if we now look at how 2 different threads could access that, I have a blue and a green pointer for that. The first one gets the length, then sets the new value, and then just gets descheduled for whatever reason. Now the second thread appears, also gets the length, and now sets the value too, but since our first thread, the blue one, didn't update the length already, the green thread now just overrides what the blue thread set in the first place. And then green just continues updating the length, and after that blue continues also updating the length. But in the end, what blue did just didn't have any effect because, as I said, green overrode it. This obviously is bad, and so we need a way to notify blue and say, hey, please stop. There's another thread currently accessing this resource. You need to continue later, and that's exactly what logs are for. For this example, I chose the possibly easiest log out there, the mutex. And with just 3 added lines, so the declaration up here and then a log and an unlog, this unlog would typically be implemented within a defer block, but to make it more visible when it appears or when it's evaluated or run, I put it explicitly at the last statement. So now again, we have our blue and our green thread. The blue starts by acquiring this log. So blue now has the permission to continue, gets the length, sets the item, and now gets descheduled again, and green appears, also tries to acquire the log, but since blue is already in the critical segment of our code, this is where bad stuff can happen. Green cannot acquire the log again and also gets descheduled, and blue can continue updating the length. And then as blue is now outside of the critical segment, it can unlock the log again, which leads to green being able to continue and running through our lines just regularly. And now green did not override what blue said initially, and we pushed 2 elements to the stack, and we can all be happy. So this is what logs for. It solved our initial problem, but as I said, we used the most simple one, the mutex. There are obviously different solutions for more complex synchronization problems or locking problems. Just to point out a few, there are, for example, semaphores, which with which a thread can also acquire like multiple locks, or the semaphore can be locked multiple times, if that makes sense. There are non-blocking locks, which is often called try-lock, which does not block the thread, but just returns false in the case that it can't be acquired. There are also read-write locks to differentiate between read operations and write operations, where multiple read operations can occur concurrently, but if a write operation occurs, then also read operations have to be blocked. There are also reentrant locks. I think in Zig they are called, or the mutex variant that is reentrant is called recursive mutex, because a thread can then acquire the log multiple times, which would not work with the standard mutex implementation. There are also phases or barriers and so many more stuff. So as I said, with different problems, you have to choose the right tools. And what we want to look at today, if logs are even the right tool at all. So there are different solutions, and this is what we will investigate, because logs do have hidden costs. It's not just, I throw a mutex on there and everything's fine. That might be often the case, but it does not need to be the case all of the time. So there are hidden challenges or hidden costs associated with that. For example, there can be bottlenecks. So if multiple, or if we have like many threads trying to acquire the same log, then all but typically one thread needs to get descheduled and only one can do work. And this just takes sometimes much time before then all other threads can proceed. There are more failure modes, which we will get into detail in, I think, a few animations. And it's easy to just think that we solved the problem by adding a log, but in practice, as I said, there might be implications which we are then not thinking about anymore. Because it does look simple, doesn't it? Just putting on lock and then unlock and then we are finished. But yeah, that doesn't need to be the case. So flashbang, I said we will look at a few additional failure modes that logs can introduce in our code base. There can be problems with contention. So contention is, as I said, when many threads do want to acquire the same log, then this will just won't work. And then all but one thread needs to be descheduled. And this just introduces performance degradation, as just one party can continue with the work and all others have to wait. We can also capture this in a more theoretical way. So you might know from school or university or wherever you have learned computer science stuff that this seems backwards. That we can like calculate the speed improvement by introducing concurrency in our program, and there's Amdahl's law for that. I'll just quickly sketch it out. You cannot read this, can't you? But is this the fault of the chalk? Maybe if I try something with more contrast, like red. Nah, that's also probably not readable. Whatever, and I'm not using the board. So in Amdahl's law, it's roughly like 1/1 minus the time that can be parallelized, and so on. And since the time that can be parallel, or that the time or the portion of the code that cannot be parallelized is like in the bottom. If it gets bigger, then Amdahl's law leads to a smaller value, so a lesser speed up, if that makes sense. So if more of our code has to wait until another part of our code is finished, then we obviously gain less speed up from our concurrency. And that's bad. If we do implement concurrency, then we want to gain as much as possible from it. Then there's starvation. That's kind of similar. I just skip over that for time reasons. Priority inversion is pretty interesting because that's often unnoted. This is when we have, for example, 3 threads. One has a low priority, the other one has a medium priority, and the third one has a high priority. The thread with the lowest priority acquires the log, then gets descheduled for whatever reason. Next, the thread that has the high priority does want to acquire the log, but cannot do so as the lower priority thread has already done so, and gets also descheduled because it has to wait. And now the medium thread gets run and preempts the lower priority thread as it has a higher priority. And H, or the high priority thread, has to wait indefinitely because L just doesn't get scheduled anymore because it has a lower priority than the medium thread. That's priority inversion. And as I said, that often gets or is unnoted because it's a bit hidden from us. Lastly, composability. Composability is when a function that how do I say that? Or a function that does acquire a log is, or it's rarely a good idea to call that function from within a critical section. And this again leads to just more coarse-grained logs. So we are incentivized to log a larger critical section, which in turn just makes all those problems even worse. And long story, short summary, are logs good? Maybe, maybe not. We will look at an alternative. This is log-free programming, so logging without logs, synchronizing without logs. We already looked at the first part. The rest of my talk will be more of a theoretical perspective, or how this whole concept of log-free programming works. Then we will look at how this can be implemented in Zig. And lastly, if it is a good solution, so for internationals here, this is the German eierlegende Wollmilchsau, which is a jack of all trades. And we will look at if log-free programming is also a eierlegende Wollmilchsau of programming. Okay, so how can we get rid of logs? The problem is our critical section. Because this needs to be guarded, this needs to be locked. So now if our critical section could be so small, so tiny, that there's just no possibility for any other thread to get in there while we are executing this section, then we would be fine. Then there would be no need for locking, as there's no possibility for other threads to get in there. And this is in theory, atomic operations just do provide this this attribute, because we say they are invisible, so they do work successfully or they don't work at all, but you cannot like observe any intermediate result of atomic operations. This is what makes them atomic. For example, there are atomic loads or atomic stores, stuff like that. And the atomic operation that's most important for us is called compare and swap, or in short, CAS. I don't know if anyone ever has said that, or CHS, CAS. This is the workhorse of log-free programming, and I have noted down, like it looks like Zig, but isn't completely syntactical correct, but it serves the purpose. So we always, or I use the pointer here, we always get a pointer to any data. We get an expected value and we get a new value. And our goal is to set the pointer to the new value, and then we return if it succeeded or not. Often, and that's also the case with Zig, there is no bool that is returned, but the old value itself. And if it didn't succeed, it's just null. But writing bool was a bit simpler. So the first step of our compare and swap operation is checking if the value of our pointer currently is the expected value. If that's not the case, then somebody has modified something, and we aren't at the state we expected to be at. So we just abort and say false. We have to try later. But if it is the expected value, then we can just set the pointer to our new value and return true at the end. So we can say like, look at this memory address. If it still contains the value I expect, then and only then, and this is the important part, update it to the new value. This is like when I need a spontaneous meeting with my colleagues, I just pop my head into their room and I'm like, do you have time currently? And if they say no, then we are kind of here, and I abort and say, okay, then I try later. And if they say yes, then I have a spontaneous meeting with them and I return true, and I'm happy. So this is the working horse, the compare and swap operation. And while this does look like a lot of code, we will see later that it is indeed an atomic operation and that it results in just one line. Great. So now we can compose this single operation to a whole loop. So this is the compare and swap loop. This is what powers most of the log-free data structures. And this matches the little meeting story I just told. So this just indefinitely checks if our compare and swap operation succeeded. If yes, then fine, we can exit the loop. If no, then we update our temporary values and then retry afterwards. We will see this later also in the Zig example I coded up. Great. And we call this optimistic concurrency because, as I said, we first try and assume that we can set the new value, which is pretty optimistic, and only if it fails, we then try again and are again optimistic and hope that we do not fail again. Yeah, this often gets wrapped into atomic variables. So we had atomic operations. Atomic variables just wrap this compare and swap loop so that you have, for example, an atomic integer where you then can set new values or add new values, load values atomically, so on and so forth. Good. The cool thing about this this log-free design is that we can like reason about different properties of it. And there are three important properties that we want to look at a bit in detail. Those are three levels of freeness. They are called, and they describe what guarantees our concurrent data structure has when we access them. So obstruction freedom is the lowest guarantee. This just guarantees that if there are no other threads, or if all other threads are currently suspended and not scheduled, then our current thread can access the data structure and can proceed with its operation. So I tried to model this as a little diagram. So data is our shared resource, thread is we, the current thread we're looking at, and other thread is just the rest of the system or all other threads in our program. So we first try to access data, but since all other threads or any other threads already are accessing our data, we fail and just return a failure is indicated by the dashed line. But then all other threads are being suspended or aren't scheduled anymore. We try to access this shared resource again, and now we succeed because there's just nobody else that blocks it. So this just guarantees progression in isolation and is the weakest guarantee. Next, there's lock freeness. And while this whole paradigm is called lock-free programming, doesn't mean that any lock-free algorithm is also lock-free on this slide, which is why lock-free algorithms are also often just called non-blocking algorithms. But that doesn't sound so exciting. Non-blocking sounds kind of bad, so I also call them lock-free algorithm. And when I'm speaking about lock-freeness, I typically mean the whole paradigm and not only this attribute, just so we are speaking of the same thing. Yeah, lock-freeness is like one step further. Now it's guaranteed that at least one thread always can make progress. So even if there are other threads working on our shared data structures, lock-freeness guarantees that at least one of our whole systems makes progress. So it is fine that all other threads are just idling or in the loop forever, but at least our thread on the top does make progress. That is the lock-free attribute. And this is typically guaranteed by our compare and swap loop we saw earlier. So whenever we have a construct like this, this is typically lock-free. And we can reason about that, because if this compare and swap operation fails, what does that mean? Yeah, that means that another thread has successfully changed the state. So another thread's compare and swap operation was successful. So there's always at least one thread making progress. I hope that was understandable. So then the last guarantee, which is the biggest, greatest guarantee, is weight freeness. Weight freeness guarantees that in a finite sequence of steps or number of steps, every thread is guaranteed to make progress. So this wasn't the case with lock freeness. There we can still have a live lock where we just are looping over and over. Weight freeness does provide that guarantee. So our current thread and all other threads are eventually going to make progress. And that's not always trivial to achieve. So there are certain algorithms or certain data structures that let individual threads, for example, reserve a certain spot in memory, which they then can access instantaneously, which would lead to weight freeness. Now the chalkboard would come in handy again, but I try to explain it just with words. Also, if you think about a queue where we have a head and a tail pointer, just using this compare and swap algorithm could lead to the tail pointer pointing to the, or could lead to a new element being added, but the tail pointer still points to the element above it, because there are two operations that need to succeed. The addition is one compare and swap, and the update of the tail pointer is one compare and swap. And if this update did not yet succeed for whatever reason, then another thread currently accessing our queue could like help the first thread and set the tail pointer to the new value, and then the original thread who did the push operation on the queue, its compare and swap would be successful in the next try. And this would also lead to wait freeness if different threads help each other to progress. But as I said, that's not trivial for all data structures. We have to explicitly take care of that and explicitly think about that, while log freeness is way easier to achieve with just this typical compare and swap loop. And those three types of guarantees is what makes log-free programming so cool, because with blocking algorithms, you got none of that. They can do whatever they want, and it's pretty hard to reason about progression guarantees with typical logs. They don't even provide obstruction freedom, at least by default, which log-free algorithms do. Good. So far, so good. That's it with log-free coding. So you now hopefully have at least foundational understanding about what is going on. The gist of it is we have atomic operations like this compare and swap. Their critical section is practically non-existent, so no other thread can observe intermediate values or can go in between operations. They succeed or don't succeed at all. And this is what makes synchronization possible without the need of logs. Good. How can we now implement this in Zig? This is probably what you all have been waiting for. And it's pretty easy, to be honest. Because those atomic operations are just a thing that our modern CPUs support. There are different flavors of those atomic operations. They are called test and set sometimes, or compare and swap, fetch and increment. Compare and swap, I already said. And they all result in slightly different instructions. Those are from the x86 instruction set. You notice that they are all preceded by log, and then the respective locking or the respective atomic operations. We can also look at this quickly in the compiler explorer, where I provided a short example. I just used compare and swap here, which is abbreviated with CMP XCHG for change. We want to swap a 32-bit integer. We want to check this pointer. If it is currently still 0, then we want to change it to 1. And if we look to the right here, then there is our compare and swap operation in the instruction set, which again is the log operation followed by compare and swap. If we would, for example, have a load or store, then there would still be this log instruction followed by the load and store. And as I said, this is executed atomically, so no other thread can intervene. Good. So log-free programming is enabled by the hardware itself. We don't have to build software support for that. We can just translate functions or instructions directly to those log and compare and swap operations. And Zig just provides built-ins for that. So remember the compare and swap operation I implemented in pseudo Zig earlier. This is just this built-in. It takes a whole lot of parameters or arguments. So the type of the pointer we want to override, then the pointer itself, the expected value, the new value, and some stuff we will look at later. And you also notice that it again comes in two flavors. This is weak and strong. I think that if you program on modern x86 hardware, there is no difference between them. But with compare and swap weak, The swapping operation can be successful, but the atomic operation, or it is possible that the atomic operation still fails despite really being successful. I think this is only the case on older ARM instruction sets, so don't worry about that. I typically use the weak flavor, firstly, as I said, because it doesn't matter, and we also, with this compare and swap loop, we natively implement the retry that would, or that the strong version would provide us. So I just opt with the simpler one. But as I said, don't worry about it if you're programming for modern hardware. This shouldn't be too different things. Good. So in our Zig code, we can just use one of those built-ins and be happy as they would be directly translated to what we saw earlier in the compiler explorer. Then from this built-in, we can now build atomic variables again, just like we did earlier in the pseudo Zig version. Zig already provides std.atomic, which contains an atomic value, which, for example, has, first of all, an init function where you can set the initial value, and then fetch and add would be getting the current value and adding the first argument to it, so we would just increment it. Those two lines would exactly translate to just this single built-in, which is atomic read and write, with the operation here and the value here, but working with like a real type and a function-looking thing is way nicer than always writing out this whole beast. Right, and we again see there's another additional parameter, just like we had here earlier. This is like the same type, and we will get to know it in a few slides. Good. Good. So now the first real working Zig example. I implemented a stack in a log-free way. This is like the classical example you also teach students. It's called the Treiber stack. The original paper called it that way. And for now, I implemented the push operation. So first, we start by allocating a new node, initializing the new node with the provided value, and its next pointer is, for now at least, null. And then we start by our compare and swap loop we already saw earlier. We use the atomic load operation to access our current head. So again, this has to be atomic, so nobody else can like intercept our load. We then set the next pointer of our new head to the current head, and then we try to exchange the current top of our data structure with our new head, but we only do so if the current top is still the top that we recorded here. So this makes sure that in this line, or in between this and that line, nobody else modified our current stack. And if that would be the case, then this check would be false, and we would just rerun the loop again, getting old head, setting the pointer again to the now updated head, and trying to exchange the pointer again. So now a question for you. I said the top needs to be loaded atomically, and we also use an atomic instruction here. But why doesn't need, or why is next not atomic? So shouldn't this also here be an atomic value that we only modify atomically? Any idea on why I implemented it how I did? Yeah. Oh, I didn't quite understand that. Yeah, exactly. So next isn't shared currently. Next just exists on this new memory space we just allocated, but nobody besides we currently can access this memory. So next does not need to be synchronized in any way. We can just access it directly. While, of course, top can be accessed from other threads, which is why we need to interact with it in an atomic way. Good catch. Just for completeness, I also implemented pop, which looks pretty much the same. We also have our compare and swap loop now directly here. We atomically load our current head. We temporarily store the next, so the second element in our stack, and then we try to swap our current top with the next element we just recorded here, but only if it didn't change, so only if it still has the old value. If this is true, then we exit the loop down here after deallocating the old head. But if it's false, then we just rerun the whole loop again and try another time. Remember, optimistic concurrency. Good. All right, so now let's look at why we need those release and acquire, and we also had acquire and release and acquire here. So why do we need those two atomic order arguments? I also prepared a little intro example for that. So imagine this is executed by thread 1. This is executed by thread 2, while both can access the data variable. I know, again, not completely syntactically correct, but it serves the purpose. While for us, this looks, or at least at first glance, this looks completely fine and completely normal. We set data, then set data ready. So now this loop can exit and use the data. This can lead to severe problems because no, it doesn't look right. The compiler as well as the CPU itself can and will probably just reorder those statements. Because while we clearly see a dependency between this data and this data ready, the compiler and the CPU probably won't see this dependency as it is not explicitly encoded in our program. So this use data could probably move before this while loop to, I don't know, for example, mask the access time or the load time that data needs or whatever, and then our program will already be faulty. And this is what we obviously want to prevent with log-free programming. As you can imagine, if we go back and look at the Zig code, if, I don't know, the load and the compare and swap instructions are interchanged or moved around, then it just doesn't make sense anymore. We are loading and comparing values that aren't current anymore, and we need to prevent this. And therefore, we do have those two additional parameters. So there are different modes that we can order instructions. So those parameters prevent certain reorderings. And for different cases, we want to allow reorderings, and for others, we do not. So there are different ordering properties or modes that we can specify. I am going into detail on 3, but there are, I think, 2 more. So there is unordered, which doesn't really provide any guarantees. I think the Java virtual machine uses that for its shared variables. There's also monotonic, which just makes sure that operations on the same memory address are always in a predefined order, but doesn't guarantee like accesses to different memory addresses. But we will look at acquire and release and acquire release. And now I already spoiled everything, but those are the 3 main ones or most important ones, and those are also the 3 that power the log-free stack that I implemented. While I am a bit proud of this visualization because I think it looks pretty nice. It doesn't really fulfill the purpose of explaining everything very good, which I unfortunately only noticed today while driving here to Munich, so there wasn't really time in redoing everything. So I'll again try to explain it briefly, and we will also again look at the example, but just to make it short. So acquire is typically used when we want to access variables. So every time we load or we read memory locations, we use the acquire. This can be thought of like getting a log where we enter a section that we do want to make sure that everything that happens before it, we already captured in our read. And we cannot move anything after the read. Release is the exact opposite. It's mostly used on store or write operations and can be thought of like an unlocking of a log where everything after should be kept after it and not moved up in our critical section. This is why the barrier is here, and like this can't pass it downwards, and here we cannot pass it upwards. Acquire and release are also combinable, where we just introduce two barriers where we can't move up and down. This is, for example, useful for this atomic integer thing I showed earlier, where we had this fetch add operation. As this does a load and a write, both in one atomic operation, it would also acquire and release at the same time. So therefore, this acquire release guarantee is there. There's another one that's even that provides even more guarantees. This would be called sequential consistency, which works pretty much like acquire release. So there are also two barriers which we can't cross in both directions. But sequential consistency would also make sure that atomic operations always occur in the same order. So even if we would have multiple operations in here, they would always have a deterministic order to them. You typically use this sequential consistency when you don't have any idea what you should do, as this just makes sure that everything works like intended, but obviously comes with a performance hit as the CPU can not optimize your stuff better. So if you then quickly go back to one of the Zig examples, maybe the push. So we had two atomic operations here. There was the load and the compare and swap. Load uses acquire because I said load operations typically use acquire, because we want to make sure that our compare and swap here always uses the most current top that's loaded there. Because where's the slide again? Here with acquire, any memory operation down here cannot move up through the barrier, and this way we always load the most current one. So compare and swap could not move before the load and access a outdated variable. And then we have compare and swap itself. We there use release and acquire. So release would be used in a successful case. So if we successfully compare and swap the value, we set a release barrier. If we unsuccessfully compare and swap, so we have to try again, we again use acquire. This is because we don't want this load to be moved before the unsuccessful case, so that we in the next iteration again have the most current version of the loaded value up here. And what have I pressed? And the release in the successful condition is used because we also want to signal to other threads that now we are finished. The top pointer did get updated successfully, so other threads then do have access to the most current value again, as they cannot pass this barrier upwards. This is roughly how those three guarantees work. But as I said, it's pretty complex in practice, and if you're unsure, just throw sequential consistency on there, and it will work just fine. Good. Until now, we only have talked about like the upsides of log-free programming. We don't have problems with contention, for example. We don't have deadlocks. We can have live logs, but if we are careful with our implementation, then we can implement it in a log-free way, which then gets rid of live logs. So I just mentioned good things about log-freeness. But indeed, nothing is perfect. And if log-free programming was perfect, then why would we have logs anyway? A pretty common example or a common problem that we can encounter with log-free programming is the ABA problem. And to make it less technical and have a little fun example, I generated 3 images of a person that's waiting in front of a red light. So this is the first state that the person observes. The traffic light is currently red, so it's blocked. It cannot progress. All right. Then, I don't know, some time passes. The light is red for a long time. The person falls asleep. But while it falls asleep, while it is descheduled, the light now is turning green, but without the person in the car noticing it. And then after they wake up again, the light again turns red, which they notice again. But for the person in the car, this state and this state is not distinguishable. You got it, from each other. They do not know that the light did turn green in the meantime. So if you now try to translate this to our stack example, we can think of like a thread wanting to pop the top element. Maybe I go back to the code here. So thread A wants to pop the top element. It executes this function. But now, for whatever reason, before we try to execute compare and change for the first time, the thread A gets descheduled because thread B arrives, and thread B pops. I would have loved to use the board for that. Thread B pops 2 values, and so they pop. Let me try something. Whoops. Okay, I try to explain it with text. So we have A and B and C. Now thread A has stored the, so A is top, and thread A stored the top so that it can access A.next, which is B later, to then set the top pointer to B again. Good. Now thread B arrives and pops A, pops B, while thread A is still suspended and not doing anything. And then thread B pops our A again. And this does not have to be logically the same A again. The only thing that's relevant for our compare and swap operation is that this pointer has the same value. And if we, I don't know, for example, use any allocator that reuses memory, it can be possible that another allocation for another node will eventually be in the same spot that our thread A remembered. So now we have the problem that thread B is finished. Our stack looks now like this, and thread A tries to continue. So thread A remembered this address. This address, for whatever reason, now matches the, or we can also call this A prime, matches the address of our current top. So for thread A, it looks like, or for the compare and change operation, it looks like it looks like this situation looks like for our person. They observe the red light, but they do not know that something changed while they were suspended. And I think in the stack example, this isn't such a huge problem, but this can have semantic issues because as the state changes and the thread doesn't notice it, it will act like the state didn't change, which can easily lead to corruption, especially if we are dealing with pointers. So keep this ABA problem in mind. There's also not a cookbook recipe to avoid this ABA problem, so you have to like evaluate and think on a per case by case basis how to avoid that. But 3 pretty common ways to avoid it are, for example, using tagged pointers. So on, or I would guess most systems are 8-bit aligned. This would mean that there are at least 3-bit that are always 0 in a pointer value, which we can, for example, use to, I have slides for that. So this is the middle part. We can use those 3 bits to, for example, store a version number. And then every time any compare and swap operation succeeds, we just update this version number and compare it in thread A's compare and swap operation. And then even if the address didn't change, the tag or version number in the pointer did change, which would be noticed by the compare and swap operation, and it wouldn't succeed. This is also possible without pointer tagging, so there exists a double compare and swap operation, but I don't think that's the case for x86. I think it's only in the ARM instruction set, but there you can explicitly like pass 2 pointers, which is here now our original pointer, the expected value and the actual value, and now a version pointer, a expected version and an actual version, which does those 2 compare and swaps atomically. But as I said, I don't think that this operation is present in x86, which is why pointer tagging exists. Another solution might be hazard pointers, but as I'm already 5 minutes over time, I'm going to skip that. Great. So now that you also have learned about a few downsides of log-free programming, so mainly this ABA problem, we can finally think about if log-free programming really is the eierlegende Wollmilchsau or the jack of all trades of synchronization. So to remember, when are logs good enough? Logs obviously are pretty simple. So when performance is not that critical, or there are only a few threads accessing a shared resource for a few times, just throw a mutex on there and it's fine. It's probably easier to understand for such simple cases than using a compare and change loop. Also, I said in the beginning that there are not only mutexes and that kind of stuff, but there also exist barriers and phases which are not only used for concurrent access, but which can also coordinate threads in general. So if you want to make sure that, I don't know, 10 threads like stop at one coordinated point, and only if every thread access or arrives at this point, then they can continue together. This would be a prime example for using logs. So I'm unsure if the Zig standard library implements such phased logs, but those aren't too hard to implement by yourself. This wouldn't really be possible with log-free programming. But on the other hand, when is log-free programming actually good? So it typically has better performance, especially under oversubscription of threads. So if there are way more threads than there are CPU cores, the scheduler has to block some threads, and if it blocks threads that currently have a lock or acquired a lock, this just makes things take even longer, since those threads cannot release the lock and have to be rescheduled again to release it. This is where log-free programming really shines. It also is not susceptible to this priority inversion, which is pretty tough sometimes to notice and fix. And yeah, also not susceptible to deadlocks, or Live logs maybe, but can be easily avoided. And especially we don't have any dumb delays because of descheduling, as we do not have to wait. We can just try again, and that might be enough to then succeed. Great. That's not quite it. TLDR logs have real often hidden problems. Non-blocking algorithms basically just use atomic operations, mainly this compare and swap, but also atomic load and store are really important things there. Compare and swap inside a loop is the main building block of different data structures. And while they do have nice properties like those freedom guarantees we saw earlier, they do also have problems. What doesn't have problems? So if I would put one statement under this talk, it would be don't be afraid to use logs, but also do not limit yourself to them. There are real use cases out there where such high performance is required and low latency especially is required, that also in practice sometimes log-free programming is used. I know of at least one banking software provider that implemented their own insanely huge log-free implementations of a shared queue, which is pretty funny because it's written in Java. Who the fuck uses Java to implement performance-critical applications? But it's really cool to see this in practice and to see how much throughput you can achieve with this kind of implementation. So thanks for attending. Thanks for listening. I hope that the technical parts didn't scare you off and you at least got the gist of it. And now feel free to ask questions.
Yes. So thank you, Lukas. This time, as it will, we will use a microphone for the questions.
Well,
Okay,
the
thank you.
question being up there, so you have to walk over there is.
Yeah, so thank you for the great talk. It was really, really great seeing you explain such hard topics in such a simple way. When I think back 20 years ago, when I played with spin logs and all that stuff, I think I read that when you use the logged instructions on x86, that they basically pause the cache line synchronization between the cores. And so when you heavily or aggressively spin in your while loops, you basically, don't you produce side effects on other cores?
Ooh, that's pretty technical. I'm not totally sure, or I haven't thought about that. But you said that cache lines do get discarded with the log instruction. Did I get that right? Mhm. Mm. Uh, mm. Yeah, that could be the case, but I'm not 100% sure about that. Did you all get the question? I'm not sure. Okay. Otherwise, I could have repeated it.
More questions.
Hey, thank you. That was really nice. I want to ask you a question about your slide where you were discussing acquire semantics with the compare and swap. The
This
one with,
one?
yeah, so the one with the code.
Yeah.
So you mentioned that the load should have, yeah, this one, thank you. This one, the load should have acquire semantics so that the compare exchange cannot be reordered above the load.
Yes.
But doesn't the compare exchange have a data dependency on old head, preventing that from happening?
Yeah, that's also true.
But so then my question then is, does it matter to use acquire? Can you then downgrade to a weaker one?
Well, we would need to test that, but by just looking at it, yeah, it could be also fine to use monotonic
Okay.
and to gain, I don't know, one cycle of performance improvement. But
Yes.
yeah.
Okay, thank you. That was helpful.
Maybe one more question before we go into the break. Yes.
I think if you speak loud enough, it might also be picked up by my mic.
Is it possible to do reallocation in a weight-free way? Because when I was playing around with weight-free or log-free or whatever data structures, I was unable to do it.
Just let me quickly pull up the slide with the different freedoms. I don't find it. So the question was if it's possible to implement allocations in a weight-free way. Reallocations. I also have not thought about that. So you said that you once experimented with that? Yeah, I need to pass on that. I'm sorry. All right. I also have a question. Why the fuck isn't this working? Did you have lectures in this hall? Am I just using the talk wrong? I mean, you can't see really anything when I'm writing there. I had like 10 examples that I would have used the board for. Well, you know what you have to check next year.
So again, thank you, Lukas, for your great talk. So we've stolen a little bit of your lunchtime. We have 15 minutes. I'm sorry for that, but we will see each other again at 1:30 p.m. here again in this hall for the third talk of the day. Test, test, test. Uh-huh. Okay, interesting. Okay, we just trying to record the talks.
Okay, so it went down.
Yeah, stream went down, policy violation. What? Yeah, but I paid for it. It's from Canva. Should be open. It should be free.
I don't know.
It should be free because I paid for Canva.
I don't know the services that I use. You give them your channel. So like I use I have Monstercard.
Yeah.
So on Monstercard for make it work to give for channel name and then so they don't copyright strike you. I don't know.
All right, then we'll just